Welcome to Year 11 using the Earth's resources end of unit test for chemistry higher tier students. Hooray, it's question 1. Water from a lake in the UK is used to produce drinking water. What are the two main steps used to treat water from lakes? Well, remember, lakes are basically quite clean, so the first thing we're going to do is filter them to get rid of the fish and the sticks and the otters. So filtration to remove the solids. After that, we've got pretty clean water. All we need to do is sterilise it, and we're going to sterilise it. Another name for that is chlorinate it, and we do that to kill the bacteria or kill the microbes. Okay. Explain why it's more difficult to produce drinking water from wastewater than from water in lakes. Well, wastewater is water that's been through the system, or it might have been through your system. So it's going to have poo and wee and whatever else you put down your drain in it. So why is that going to be more difficult to produce drinking water from than lovely water from lakes? Well, I've got 3 marks to get here. So the first thing we're going to say is quite simply it's going to be more difficult because more processes are involved. I've got to do more things to the wastewater than I do to the lake water. Why have I got to do more things to the wastewater than to the water in lakes? Well, because, look, that's because, very useful, wastewater contains more solids. Okay, put it bluntly, it contains more solids, more nasty things in it, not just otters and fish and sticks. Poo, which we call sludge. Why else is it more difficult to clean? Well, it's going to have more bacteria in it, obviously. And finally, it might have dangerous chemicals in it. People put all sorts of things down their drains, and those things go into the wastewater and have to be cleaned out before we can drink it again. So 3 marks. The first marks for processes, and then the next 2 marks for any of those 2 things. Fabulous. Some countries make drinking water from seawater. Yes, they do. Complete figure 1 to show you how you can distill salt water to produce and collect pure water. Label the following: pure water and salt solution. Okay, so they start you off with a bit of the diagram, okay, which confused most people and expected you to do a simple distillation apparatus out of it. I don't think this is a great question because there's clearly no room to put a condenser in there, but you didn't actually need to put condenser in there, as it turned out. All we're going to do is we're going to turn this into a conical flask. Okay, the conical flask has got a bung in it with a tube out like this, around there, and we're going to put a beaker here to collect the condensate. Then all we're going to do is we're going to heat the salt solution. Okay, we don't need to draw a Bunsen burner, we just put heat and an arrow like that. It would have been better if I'd labelled salt solution up there, wouldn't it? But I wasn't really concentrating, it's quite late. So I boil the salt solution. The salt solution, the water in the salt solution evaporates, it turns into a gas. The gas comes around here, it cools down. When the gas cools down, it turns back into a liquid, and the pure water arrives in this beaker here. Some people were fancy and put on a condenser around here like that, which you could do. Okay, and label that a condenser. And that has the cold water in and the cold water out to cool this tube, to cool the gas down, but you didn't really need to in the mark scheme. It's a bit of a weird question. There you go. What did people do wrong? Okay, in a scientific diagram, if you draw a line over a pipe, like, what did people do? Oh yeah, I know. So they had their conical flask maybe like that, and they had the bung in it like that, and then it came around like that. Okay, it goes down like that. If you draw a beaker, a container like that, with a circle on it like that, okay, from a scientific diagram point of view, nothing can get through that sealed line there, right? So that is a sealed system. So when I heat the water in there, it turns into a gas. There's nowhere for the gas to go. Eventually this explodes under pressure. Okay, so lots of people will have had the cryptic message, no seal. Okay, so you must be really careful when you draw diagrams, you draw scientific diagrams, that the gas or the water can always go through unimpeded without being stopped. As soon as I put a line through there like that, okay, the water, you're saying that the gas can't get past that line, and in this case, if I heat it up, it's going to explode. What's next? Okay, yeah. How could the water be tested to show it's pure? Okay, there's a nasty question because you didn't know this really. Well, you should have well, I don't know, maybe you should have known. But this was in the unit that we're doing now, isn't it? Analysis unit. The expected test for pure water was nothing to do with universal indicators and all that jazz. What it is, all we're going to do is going to heat the water until it boils. For a mark, and when it boils, if it's pure, it will boil at exactly 100 degrees C. If it's impure, it will boil at a temperature greater than 100 degrees C. Next question. Why is producing drinking water from seawater expensive? Well, if you think back to the two ways that we know about creating drinking water from seawater, it's either got to be via distillation, which requires a lot of energy to boil the water, to vaporise it, turn it into a gas, leave the salt behind, then we've got to spend energy cooling it down before we can turn it back into water again. The other way to do it was with a reverse osmosis or a high pressure filtration system, and again that requires a lot of energy. So why is it drinking water from seawater expensive? Because it requires lots and lots of energy. And that's 11 marks.